This video is going to talk about pressure at depth and a little bit about gauge pressure. It's going to tie all this back into Bernoulli's equation, or Bernoulli's, when we talk about Bernoulli's equation, it'll tie into this. One more thing about this, pressure at depth. The water's not moving. So the condition for using our relationships that we're going to determine is the water's not moving. First, let's look at what happens when you move something underwater and go deeper underwater. So without saying anything, think about how the shape of the bubble would change as it moves from letter to letter. In other words, the bubble at A, if I move it down to B, does it get bigger, smaller, or the same size? As I go from B to C, compared to A, or let's go over to B, what's going to happen when it goes from B? Will it be the same size as B, larger than B, smaller than B? Now as I move the bubble back up to D, let's compare that. Will it get bigger than C? And how will that compare to A? Would it be the same size as A, larger than A, smaller than A? And what about E? E's under the ground, kind of tucked in there. What's going to happen to it there? Is it going to stay small? Is it going to get bigger than A, same size as A? What's going to happen to the size of the bubble? So think about it for a moment. Hopefully you thought a little bit about what's going to happen. If you need to think more, pause the video. But let's see what happens. If I take the bubble at A and I move it down, it's getting smaller. So the pressure is increasing, it's squeezing the bubble. And as I move over to C, it's the same size. It's way underwater and it's squeezed still. As I move up to D, I'm the same depth below the water line as A, so it's the same size as A. And E, even though it's tucked in this little spot right here, it's still underwater. It's underground as well, but the pressure is going to be the same as it was as A, because it's the same depth from the water line. And it happens like this because pressure works in all directions, not just downwards, but also sideways and up. So, as you go down in the depth of water, the pressure increases. This causes the bubble to get smaller. As you go up, the pressure decreases and the bubble gets a little bit bigger. And even though I'm tucked under the ground, the depth from the water line stays the same as compared to A, so the size of the bubble is the same as compared to A. Now let's look what happens when we stack up our pressures. So let's talk with something we know a little bit more about. Let's talk about weight first and force. So if I've got my hand out and I put a box in it, then I can feel the force that's on my hand is equal to the weight of that box. If I add another box or two, the total weight on my hand is just the sum of the weight of each of the boxes. That kind of makes sense. So the total force that's on my hand is equal to the total weight, which is the weight of each one of these boxes, because weight's a force. What about pressure? Well, pressure is just force over area. So I can take my same relationship and I just divide everything by the appropriate area. And that tells me the total pressure on my hand, where the pressure at the bottom of the stack of the boxes is equal to the pressure due to each box above. That's the weight divided by the area. So in other words, the pressure at the bottom is sum of all the pressures above. Now there are three ways we can determine pressure. One, you can just be given the pressure, call it P subscript 0 or P naught. So they could just give you the pressure. Oh, the pressure is 100,000 pascals. Just give it to you outright in a problem. A second way is a new way of looking at it, and it reflects back to what we knew about the bubble. Pressure is rho g h, where h, it isn't really height so much, it's more like depth. But it's the height you'd have to go up to get to the water line if you're below the water. And we'll show a little example of that in a minute. But that's the second way of finding pressure. And the third way is our original way, force over area, which in this case would be weight over area. So three ways to find each one of those P1s, P2s, and P3s. All right, let's look at a little visual example of this. I've got a cylinder with some water and a ball underneath it, and some kind of a fluid in the cylinder. And the ball has to go up some height h in order to get to this water line. So even though we're talking about depth, we'll call it the height to the water line. And the pressure on the ball is equal to the sum of all the pressures above it. So the first pressure is due to the atmosphere. So we'll call it about 100,000 pascals. That's the pressure of the atmosphere. The next pressure that I have to add to that, remember it's like stacking those boxes, so I'm stacking up all the pressures. So here's the pressure above it, it's equal to 1 atmosphere. The next pressure is due to the fluid and the height, or the height has to go up to get to the surface. And that was rho gh. Looks a lot like potential energy. It's kind of related in a way. So I've got this, but I've got rho gh. The density, g, and the h. So the total pressure at the bottom is equal to the sum of all the pressures above. And the pressures above are P naught and rho gh. So that's the pressure at the bottom. So we're talking about pressure at depth. Rho gh is the pressure due to the fluid above. P is the absolute pressure. P naught is the initial pressure or pressure at the different location. Remember, as I add up my pressures, in this case I had 2 above it, one due to the atmosphere and one due to rho GH. Rho is the density of the fluid, and G is just 9.8. It's not negative, it's positive, 9.8 meters per second squared. And H is kind of a weird way of saying it, but it's the depth of the fluid's top to the object. In other words, it's how far underneath that water line it is.